All right, let's go ahead and get started. Um, as possible. Oh, yeah. Make sure you. The last time, and I think we decided that it looked like it had some part of. So let's look at it a little different way. So I think the way that we said this last time, and I kind of erased most of what I had before, but if we talk about the sequence we were looking at, I think it looks something like this. After the first dose, we have 0.2 milligrams per milliliter, then 0.26, then 0.278, and then if memory serves 0.2834. So that's if I write it as a sequence. But then what if I think about these terms? What if I try to express them as a sequence of partial sums? So is it clear how I'm getting from this thing up in the margin to this one here, the 0.2 plus 0.06? Saying this build out. If we look at these terms inside the brackets here, do we notice anything about the relationship there? How do I get from 1 to 0.3 and then from 0.3 to 0.3? Multiply by what? Do we agree that this is going to be repeatable? So then the next term would be what? Should be 0.027, right? I believe if I add 0.027 to this, I mean, I'll get the next term. I don't think I remembered it correctly. So what is 0.278? 0.278 plus 0.027 is 0.05. Oh, we have to multiply that by 0.28. 0.305 makes sense. So actually, it seems like that jump is pretty big. It is 0.2834. So how did I get that? Let's back up since I kind of lost the train of thought there. So all of these terms here. So yes, this is a geometric sequence, a geometric progression. So this term right here should be 0.027, right? So what is 0.027 times 0.2? That is 0.0054. But what do I want to do with that 0.0054? I want to add it to this term here. So that's kind of where that appearance of this additive thing going on is, because in a series I am adding all these terms together. But if I express this series in a careful way, I can see that it's geometric. We okay with how I got here? Okay, so this is a geometric series. is this going to have a convergence? Well, actually, first of all, let's do the second bullet here. Can I come up with a formula for this series right here? So the sum from n equals 1 to, actually, no, I want this to be partial. So from I equals 1 to n. Did we talk in general last time about how to express geometric? So what makes a series geometric or a sequence geometric? Common ratio, right? And what do I do with that common ratio? I basically just keep multiplying by it. So I think I minus 1 is what I want. Yeah. But is this complete? So is this alone going to give me my full series? So the first one. Two needs to be there because basically I'm going to multiply all those terms by subformula. So in reality, my first term is not 1, it's 0.2. And my second term is not 0.3, it's 0.3 times 0.2. So I think I can generalize the series this way. Any questions on how I defined the general series? Can I find the sum of this thing? How do we know it exists? Right, so it's strictly between -1 and 1. So this thing better converge, which means I can find this value. How do I find it? How do we find the infinite sum? One minus r, which is 0.3, right? So I should get 0.2 over 0.7. And just for good measure, let's approximate that. I think that's about 0.286. So even after 4 doses, we were getting very close to that, right? So that's that 0.286. We're going to get arbitrarily close to that. All right. Can I write a fraction for this number here? So 1/7 repeats. Representation, right? That's kind of a giveaway. This thing should be equal to some integer a divided by some integer b. Any ideas on how we can use the tools of series, geometric series specifically, to get there? I would really, really like it if I could add a bunch of things together. What am I adding together? I think I have 2.3. So let's start this. What is 2.3 plus 0.017? That should give me this right here, right? 2.317. What can I add to that to incorporate these next two digits? 00017. We okay with that? What about the next ones? 5 zeros? Okay. Is there a geometric series here? I think we have to be a little careful to find it, but where is that geometric series? How can I define it? As the power of n plus 2? Oh, 1 over power of n, or 1 over, so 1 over 10. So to get from here to here, I'm multiplying by what? 100? Is that fair? Is this also true? What about this one? I don't think that fits, right? So I think we do have a geometric series here, but I think we have to be careful about, what we invite in our definition, because I think the common ratio applies for everything. So basically, it applies to all the stuff that repeats, right? That repeats are converged. Leave off the 2.3. If we define this thing, we have 2.3 plus some series. So from I equals 1 to n, can we define the terms in this series? We know the common ratio, right? What's it? 1 over 100. So what am I going to raise that to? So the last one we just did, we did I minus 1. I think I want to call this one. What else do I need to incorporate in this definition here? What's the first term? 0.017? Yep. 0.017 times 1 over 100 times, or to the power of I, right? Is this going to work for what I want to do with it? I think it does need to be I minus 1. But I want the first term to be 0.017, right? Which means I want the first power on 100, 1 over 100 to be 0. So we got a geometric series. So first of all, do we agree that geometric series does the thing that I actually want to capture? So I'm going to capture that repeating decimal pattern. Okay. Is it going to converge? It should, right? Because? Right, so the ratio is in between -1 and 1. I don't think I showed this last time, but you might have also seen this representation. If the absolute value of the ratio is less than 1. That's an equivalent way to say that R is between -1 and 1. So now that we have that, we agreed that this thing here has a sum. So how do I find that sum? The infinite sum of a geometric series is what? First term divided by 1 minus the common ratio. So first term is 0.17 over 1 minus 1 over 100. So I got 2.3 plus 0.17 over, and I got decimals mixed in with fractions here, so we're gonna have to start changing some of our definitions here. So let's start converting these things to fractions. What's a good fraction representation for 2.3? Oh yeah, I missed a, thank you. 0.017, thank you. All right, so now we're dealing with the right numbers. You ready? Sorry, so zero. Oh yeah, the geometric sequence at the time of ratio. All right, so now represents 0.3. If you over 10, can represent 0.017 as a fraction. Let's just get this in line. 17 over 1,000 over 99 over 100. Okay, where do we go from here? How do we divide fractions? Okay. Is there a way to add those two things together? We can do that. So then this becomes 2310. And if I divide this thing by, if I both divide the numerator and denominator both by 100, I get 17 over 990. Two two seven seven. So 2277 over 990 plus 17 over 990. So that very obvious fraction comes out to be this same decimal representation. I don't think this, yeah, I don't think that reduces. Unless, no, I don't think it reduces. Never mind, they're both even. So what is 2294 divided by 1147 over 445? 95? Oh, sorry, thank you. 890. So a long way to go. Any questions? How we got there? This one is deceptively complicated. But yeah, if I ask you to reduce it completely, I'll hopefully it'll be more cut and dried. How we doing? All right. So now let's bring this in. What is maybe we can see what's going on here by looking at the first few terms here. What's the first term in this sequence going to be? 1, right? So where does this series starts with what value then? 0. So it's a little atypical. So first term 1, what's the next term? X followed by so continuing to inflate like this. I want to find a sum of that's something to do. What kind of series is this? So if you're telling me it's geometric, it must have a common ratio. What is it? Should be X, right? So R is equal to X. Does this thing converge? No. Why not? How do you know? I've told you that X is the absolute value of X is less than 1. So that is the only condition by which a geometric series converges, right? Is that the ratio, the common ratio, has an absolute value that's less than 1. So since I've guaranteed that X is going to be bookended, we're going to be bounded below and above by -1 and 1, we can guarantee that, right? So now we should be able to you should be able to find the infinite sum of this thing, this geometric sequence. Any guesses on, or any ideas what that could be? Did you get that? Right. So, and this is, yeah, so the sum of a geometric series has not changed. So it's always the first term divided by 1 minus R. What's our first term? 1. And our geometric series, or common ratio, you already said was X. So yes, this infinitely long series, as long as X is in that. Something I showed you was, I think we talked about this function, f of X equals the natural log of 1 plus X over 1 minus X or something like it. So, and I said that like that log term, like like this. So this is like continue. Okay. So getting away from geometric series for a bit, still series though. I want to show that this series here converges. So is this, we're probably going to see that that doesn't. But so let's get a few terms. What is the first term of this sequence going to be? 1/2. How about the next one? Moving on. think I have a typo in here. So 1/2 plus 1/6 plus 1/9, right? So 1/9? 1/12? So I am convinced it converges. I think I have a typo in here. I wonder if I meant this 1/n plus 1. Now I think I have another one of these. So let's do this. I'll come back to that. I'll figure out what I meant to say, but I know I have a typo there, and I don't want to guess at what it was. So I'll come back to that. So I want to show that this series here diverges. So can we look at the first few terms in this sequence? So, or in the series. So it should go 1 plus 1/2 plus 1/3 plus 1/4 and so on. Actually, let's write out a few more. So this thing, it's a pretty common sequence. This is what's commonly known as the harmonic sequence. And it's kind of counterintuitive because it seems like, let's just think about the sequence. And I think this is even a sequence we've talked about. What's the limit as n goes to infinity of 1/n? I know the sequence goes to 0. But I'm also telling you that as n get really large, why is that? So let's start grouping terms up. I have a 1 here, and I have a 1/2, right? So basically, the way that I'm going to think about this is, let's start collecting things that are at least as large as a 1/2. So I have a 1, right? And I have a 1/2. These next two terms, what is 1/3 plus 1/4? I don't really care exactly what it is, but I want to know, is that at least 1/2? More than a 1/2, right? So this is more than a 1/2. This is equal to a 1/2. This is more than a 1/2, right? I think I needed one more here. And this is maybe not the most rigorous way to show this, but hopefully it convinces you at least. Now, so I got a 1/2 out of this. What about the next 4 terms? If I add those together, I don't even know if I need all 4 of them. What is 1/5 plus a 6 plus a 7 plus an 8? Okay. Okay, so greater than a 1/2, right? So even though the terms are all getting smaller, so 0.5, 0.3 repeating, 0.25, 0.2, 0.17, 0.14, they're all getting smaller, but the rate. So basically, no matter how far out I go, I can always group up some number of terms and get another 1/2, which means I will never settle out on a convergent sum for this series. So this is one of those, counterintuitive sequence or series that, even though the sequence goes to 0, adding up all the terms in that sequence cannot be done. So any questions on kind of the logic I'm using to show you here, Colin? Correctly. That's correct. As opposed to um, we can say that this converges. I don't remember what the sum is. The sum is something like, it's something like, I don't know. I don't want to guess what it is. It involves pi. Does converge to something. So that, once you have a power, and really don't ask me to prove it, but I can tell you that as long as this power up here is bigger than one, plus all of them. All right. So I have this, I think we've talked about this a little bit, but let's revisit. I have this series that converges. If I know the series converges, what does that tell me? Sequence I get. The list of the what? It should converge. Can we do better than that? It should converge to zero. Are we okay with that? Let's say you had a sequence that converged to L. I don't care what L is, I just care that it's not zero. Is it possible for that sequence or that series to converge? If sequence conversion. Something that's not zero. Then essentially I'm adding L several times, right? And if L is not zero, there's no way that sum can converge. So this is one thing we can say for sure. If my series converges, I know the sequence. If I have a sequence that goes to zero, does that mean that the series converges? No, why not? Yeah, we just talked about that. And that's a really important thing in one. If you have a series that converges, sequence has to converge. But if you have a sequence that converges to zero, you can't yet say it's more limited. So, and that's this divergence theorem here. So for most of the rest of this, this is kind of like your first. So this series diverges. So let's check for the sequence what it does. So what's the limit as n goes to infinity of, not the series, but sequence? N squared over 5n squared plus 4. Is this a limit that I can look at? Well, that false. I'm something else. Didn't we have any like gut reactions or feelings about what this was going to do? Converge to 1/5. What makes you say that? Okay. So I have the largest power, the largest degree in both is the same, right? So here's what I'm going to do. Hopefully this is another way to convince you. Can I do this? Basically multiply numerator and denominator by 1 over n squared. Is that legal to do? I know I'm never going to divide by 0 doing that, right? N can't be 0. So what happens if I make that adjustment? Then I have the limit as n goes to infinity of 1 over 5 plus 4 over n squared. Is that a limit that I can evaluate? What happens as n gets really big there? Doesn't go to 0. So yes, the 4 over n squared goes to 0, which means what remains is 1/5. So does the series diverge or converge? Right? Because why? You were so close. I think you try saying that again. I have a big protest about one of the words you used. Sequence does not converge to 0. So, and I know that sounds nitpicky, but the sequence and a series are very closely related things, but they are different in a very important way. So since the sequence goes to something that's non-zero, that means in the series, essentially, I'm going to be adding numbers together that are really close to a fifth over and over and over again, which means my sum is just going to keep getting bigger. Any questions there? Okay, so I want to go back. I found my fix here, or at least I found something that'll work. So 1 over n minus 1 over n plus 1 is what I want. So let's make the fix. All right, so let's try this again. So I want to look at the first few terms in the sequence, or in this series. I think I can erase these, can I? Nope, they're stuck. So disregard. Now let's find the first few terms in the sequence, or in this series. What is the first term? Okay, so for now, I'm going to keep these things separated. 1 minus 1 over 1/2. What's the next term in the sequence going to be? 1/2 minus 1/3. Let's get 2 more pairs here. 1/3 minus 1/4. Plus 1/4 minus 1/5. and so on. Actually, let's have this terminate at some. I'll write it the last two pairs here. So yeah, if I do a partial sum here, I'm going to have 1 over n minus 1 over n plus 1. So what would the term before it look like? 1 over n minus 1 plus 1 over n. Do we notice anything about what's going on in this? So let's just look at the early part of the series. So in this row here, if I start summing up those terms, like what's going to happen? So let's start at the 1 minus a half plus a half minus a third. What's that going to come out to be? 1 minus a third, right? Because these inner terms are going to cancel, right? What about when I move on to the next pair? Same idea, right? The thirds are going to cancel, then the fourths. So, and then that's going to continue indefinitely. That should be a negative sign. So this is going to cancel as well, right? So basically what you're going to be left with is the limit as n goes to infinity of 1 plus 1 over, oh no, 1 minus that. 1 minus 1 over n plus 1. So why can I say? Basically, I'm making the claim that no matter how many terms of this that I write out, only the first term and the second term are going to remain. Everything else. What does this limit come out to be? Should come out to 1, right? So these kinds of series are called telescoping series. And the piece in the lens. Everything else. So, and kind of look when we we'll actually be able to find out what. For example, like there are lots of things in math that we know the existence of, but it doesn't mean we can find it. So for example, I believe that this was proven hundreds of years ago that it converges. I don't think it's known what the sum is. I believe that's still true. I think the last thing I had on here was another example of a telescoping series. Yeah, we'll go ahead and stop here. So I'm ending a few minutes early. I think I told you I was going to start section 8.4 on Friday. come ready with it. Here we go. A little bit.